In this series of videos, we are going to talk about the areas of trapezoids, rhombi, and kites. To begin with, let's talk about the areas of trapezoids. For this, we are going to need to define the height of a trapezoid. That is the perpendicular distance between the bases. Because parallel lines do not intersect, the distance between them is constant. So that makes this the perfect distance to use as the height of the trapezoid. Knowing that, let's now talk about the formula for the area of a trapezoid. Whenever we work in geometry, we like to split up figures into things that we already know, and something that we already know are triangles. We know how to find the area of triangles. So by drawing a diagonal in a trapezoid, we separate it into two triangles. Each triangle has a different base. So we'll call one base sub 1 and the other one base sub 2. Remember that these subscripts don't mean anything mathematically, only that we have two bases, so we're trying to keep them straight. Now both of these triangles happen to have the same height. The distance between the parallel lines is the same, so therefore the heights of the triangles are the same. So the area of the triangle in the upper left is 1/2 base 1 times h, and the triangle in the lower right has an area of 1/2 base 2 times h. Now a lot of people like using this idea that it's the area of these two triangles, and that's perfectly okay. However, there's something that's much easier to remember. Notice that both of these terms have 1/2 and h in them. So we can use the distributive property of multiplication over addition in reverse, and pull this 1/2 and this h outside of parentheses, giving us the area of a trapezoid is 1/2 the height times the sum of the two bases. That's much easier to remember, and it's the one I encourage you to use because it requires the fewest number of calculations. The area of a trapezoid is 1/2 the height times the sum of the two bases. So now let's use this. You will notice that the drapery at the right is roughly a trapezoid. We can superimpose a trapezoid there. It is 2 feet wide. The long base, that would be the right side, is 6 feet long, and the short base, the left side, is 2.5 feet long. And 2 feet of the panel is doubled at the top. So this area up here, you can kind of see this, that it's doubled up here. So how much fabric will be needed to make the matching panel? Well, the first thing we probably need to look at is this area that's doubled at the top. You'll notice that it's 2 feet by 2 feet, so that's a square. The area of a square is just simply a side squared, so 2 feet squared is 4 square feet. So that's the area of this top part. Now let's find the area of the trapezoid itself. That's going to be 1/2 times this 2 feet, that is the height of the trapezoid, times the 6 feet plus 2.5 feet. So using the order of operations, 1/2 times 2 feet times 8.5 feet. And of course, half of 2 feet is 1 foot, and 1 foot times 8.5 feet is 8.5 feet squared. Notice how if we use our units in our calculations, then it's all going to work out at the end. All right, so we have this 8.5 feet squared, but we also have the 4 feet squared from where it was doubled over. So that's 12.5 feet squared. But now let's look at this one last time. Notice that the panel itself is doubled over all the way through. Okay, there's a little bit here that isn't quite doubled over, but nonetheless we're approximating, so this is going to be fine. Since it's doubled over, we need to double that. So we're going to need a total of 25 square feet of fabric to make the matching panel. Now sometimes they're going to, the fact that segment AR is perpendicular to both the bases, but it's not labeled with any length. So a lot of people will be tricked into believing that there is no height here. However, look at this 60-degree angle down here at the bottom. If we were to draw in a height, let's label this point down here E. If we were to draw in a height from point P, let's label this point down here E. Notice that we have a 30, 60, 90 triangle. So let's take a look at quadrilateral APER meters. Quadrilateral APER. Notice that it is a rectangle, and opposite sides of a rectangle are congruent. So segment AE is 120 centimeters, which means that segment ET is 70 centimeters. We just found the short length. So we can easily find the long length now because the long leg is the short leg times the square root of 3. So segment PE and also segment AR happen to have a length of 70 times the square root of 3 centimeters. We now know the height of our trapezoid, so we can find the area. The area is going to be 1/2 this 70 times the square root of 3 centimeters times the 120 centimeters plus the 190 centimeters of our two bases. Order of operations tells me that 120 plus 190 is 310 centimeters. And I'm going to take half of that to make my numbers smaller. So I have 70 times the square root of 3 centimeters times 155 centimeters. And of course everyone knows that 70 centimeters times 155 centimeters is 10,850 square centimeters, and then let's tack on our square root of 3, and all is well. The area of our trapezoid is 10,850 times the square root of 3 square centimeters. So the area of a trapezoid, quite easy. Take the lengths of the two bases, add them together, multiply that by the height of the trapezoid, then divide everything by 2.